welcome to EMS Physio. Today we're looking at the process of building a transducer, starting with measuring the frequency of the crystal that we put into the steel. So every crystal has to be measured independently. We place it on this little table, and what we're looking for here is this resonant frequency indicated by the scope suddenly dipping down at that point. So we now use this function generator to move that line across on the scope until it aligns with the dip. There, and that is telling us that the frequency of this particular crystal is 3.4910 megahertz. So we've now recorded the frequency on the crystal. The next stage is to determine the correct thickness of the steel that will be required to work correctly with this crystal. So we've got a simple chart here, and we're looking for 3.491, which is going to be about here, and this will tell us the thickness of the steel that we need, 2.49 millimeters, which is what's recorded on there. The next stage now is to go and grind the steel to match. So now we're taking a batch of steels and we're preparing them for bonding the crystals. First thing is to get the thickness of the steels to match the frequency of the crystals they're going to be paired with. So we're measuring the thickness at that point and calculating how much material we need to remove in order to achieve the desired thickness. And this has to be done on every steel and every crystal assembly to make sure that they respond correctly. So the steels are placed in groups of 5 or 6 into this, in this case only 3, but that's fine, into the grinding wheel. And there's a timer on here, and Bill knows approximately how many minutes he needs to grind to remove the required amount of material. Away we go. So some grinding fluid is applied, which is a mix of oil and aluminium oxide powder, which will slowly polish that steel until it gets to the right thickness. This could take 5 to 10 minutes, depending on the amount of steel that needs to be removed. So the crystal is now bonded into the steel, cured in the oven, and the front face of the steel is polished. This is actually not a brand new steel, but it's just been used for the purpose of this video. What we now do is we check that the crystal is still responding as correctly now that it's bonded to the steel, and it's bonded to that steel with a conductive adhesive which contains silver. So we place that on there, and you can see we've got this same resonant point, and we can adjust to line up with that. And we're looking for a figure here that is somewhere between 3.2 and 3.5, and we've got 3.350. So that is acceptable and ready to go. So the steel and crystal assembly has now been fitted to the transducer. We're going to test the output on this precision ultrasound balance. It sits on there so that the transducer is in contact with the water, and there's a reflecting target inside that force balance. You can zero that, and we're using 3 megahertz in continuous mode, and as we increase the intensity, it shows us here the watts in square centimetre. So we've got 1.5 watts per square centimetre. We know we've got a 4 square centimetre steel on this transducer, so we should be seeing about 6 watts. And we can see this a little bit low, 5.72, but that's within the normal tolerance of 20% in fact. If we remove the transducer from the balance and the water, we should see a contact alarm once the water is evaporated from it. Two of the other important features to measure in ultrasound are the ERA and BNR. The ERA is the effective radiating area. The BNR is the beam non-uniformity ratio. Both of these values are determined and set in the International Standard 60601-2-5 for therapeutic ultrasound devices. So what we use to determine that is an ultrasound scanning tank. So we've got a transducer in this tank which is submerged in water, and there's a hydrophone which is picking up the signal or the output from the transducer. And if we start the tank is now going to move backwards and forwards and slowly begin to traverse the entire face of the crystal, of the steel rather. Now that's a 4 centimeter square transducer, and it's taking a measurement one for every millimeter. That should be somewhere in the region of about 1,256 individual measurements are taken to determine the output at different places of the transducer. This actually takes about an hour or so to complete. By the time it is complete, we can use the data that we've gathered to present a three-dimensional graphical illustration of the output from the transducer, which shows that we've got a nice uniform wave there. What you don't want to see is one that is skewed to one side or very tall and thin, which would indicate a hot spot in the middle. So this is a nice uniform distribution of the power over the entire front face of the transducer. Today we're testing the stimulation outputs of combination PCB. So this is a PCB that would go into the EMS860, and we've got a test setup here with a digital multimeter on the right hand side, which is showing the output in amps, and we've also got an oscilloscope at the back there, which is enabling us to see the waveform and the pulses that are being generated by the board. So this is a sort of semi-automated test that each board goes through, and it will cycle through all of the different waveforms and the different outputs, and the engineer verifying the tests will look at each one independently and check that each output from each waveform is generating the right intensity. So here we are testing this PCB in interferential mode, constant voltage, and you can see channel A and channel B are both set at 58 volts, and the oscilloscope over here shows that interferential waveform, and this is measuring peak to peak.